Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 50, and this problem asks us for two parts. First, explain why protonation of pyrrole, this molecule here, occurs at carbon 2, right there, to form A, and not on the nitrogen atom to form B. Then it asks in part B, explain why A is more acidic than C, the conjugate base of pyridine. So let's first tackle A. So protonation of pyrrole can occur at two sites. One on this second carbon 2 to give now compound A, and one on the nitrogen to give compound B. So why is it that the protonation occurs on this carbon 2 and not on this nitrogen here? So let's tackle this question. Well, let's talk about aromaticity and resonance. So if we get protonation on this carbon 2, we can actually draw some resonance structures now. We can show that these two nitrogens now go to the nitrogen nuclei to neutralize it, giving us one resonance structure like this. And now this carbocation now moves over to this carbon over here. But now we can move around that carbocation once again around the ring to over here. So now what we see is that this conjugate acid A, we have delocalization of this positive carbocation around the ring due to resonance. So because of that, we have some sort of stabilization effect that occurs from this resonance stabilization of the delocalization of this positively charged carbocation that originated on the nitrogen nucleus, but we're now moving around this ring. Carbon or compound B, we see here that we can actually move any electrons around to delocalize this positive charge. If I were to move this double bond here, well, yes, I will get a carbocation here, but now I would get a nitrogen with 5 bonds. And already nitrogen with 4 bonds has a positive charge. So nitrogen with 5 bonds, that is not happening. So there's no resonance structures with compound B. Because there's no resonance structures with compound B, there's no resonance stabilization of this carbocation charge on this nitrogen atom. Therefore, because there's no resonance stabilization, this is what we call a very hard charge. But here, because this charge is actually being delocalized around the ring, we have some sort of stabilization effects from that, and that is why protonation will occur on carbon 2 and not on the nitrogen atom. So now moving on to B, B asks us for why is A more acidic than C? So let's draw compound A again. So when we talk about acidity, we need to talk about what is an acid. So acid is something that gives up a proton. So it loses a proton, or you could say it gains electrons. So in this example of losing protons, well, if we lose this proton that got added to carbon 2, we see that now the 2 electrons that are in the sigma bond will go onto this carbon-carbon double bond, making a bond. When you make a bond, you break a bond. So this double bond will break here. When you make a bond, you break a bond. So these 2 electrons will go onto the nitrogen nucleus. Now we get the conjugate base of this acid being pyrrole. So we reform pyrrole here. So when we reform pyrrole, what we see is that the 2 electrons that fell on the nitrogen atom now, these 2 electrons are actually in the p orbital that goes up and down. Therefore, we know that these electrons can delocalize around the ring. So in total now, we have 6 pi electrons. So therefore, pyrrole is aromatic, following the 4n plus 2 rule for number of pi electrons. Therefore, because it has 6 pi electrons, this can delocalize around the 5-member ring, making it aromatic. So deprotonation of this acidic form of pyrrole is actually a highly favorable process because we form an aromatic compound being pyrrole. But now what about C? So C, if you start with this molecule, we see that already we have 6 electrons. So already this is an aromatic. Follows the 4n plus 2 rule. So if we were to deprotonate this, we would get pyridine that looks like this. But pyridine already, the conjugate base already still has 6 pi electrons. Why is that? Well, now those 2 electrons that are on the nitrogen nucleus, they're on the plane of carbon-carbon bond, so they're not in the p orbital that goes up and down, so they cannot delocalize around the ring. So these two lone pair electrons are not involved in the calculation of aromaticity, so we only have 6 pi electrons. But the starting material, the starting acid, already has 6 pi electrons as well, so we're not actually gaining any aromaticity. This molecule was already aromatic to begin with. So because we're actually not gaining any aromaticity, we're not actually gaining any stability in this conjugate base. Unlike in A, by losing this proton, we actually gain or we form an aromatic compound, gaining stability. So this is a highly favorable process, meaning that A is much more acidic than C.